And then the other example, and I think, I mean, in this case, it may be a little better to use the animation for that. So it's an atomic layer deposition process. And atomic layer deposition is again something that you've probably done in your childhood, making these type of sand paintings, whereby you wanted to create this colorful image. And what did you do, or how did you approach this? Well, you made your drawing first, so that's your pattern substrate, and then you applied some glue on part of the surface. So you created reactive sites, and then you did put on some colored sand, and obviously the colored sand remained at the places that were activated, that were glued. So you were creating the shape of the dolphin in there, and then you basically flipped the painting over, and all of the non-reacted sand basically fell off, and you had a very nice exposure of the dolphin image. Well, this is what atomic layer deposition is also doing, but then in a chemical way. I mean, you can then continue with other colors, and then you have that very nice image, or at least, I mean, it depends on how good you're in drawing and in gluing, but the same is true for atomic layer deposition. So you basically have two precursors and a surface. And I have my surface, and I allow precursor 1 to come in, and precursor 1 will react with the surface. So that's the glue part. Only where my surface is activated, my precursor will react. So there will be a chemical reaction between the precursor and the surface. Then I have this stage of flipping the paper. So whatever sand that did not react falls off. Well, the same is true. I'll just have a neutral gas purging all of the non-reactant precursor away. In an ideal situation, I end up with a situation where all of the activated surface is now occupied by precursor 1. And then I bring in a second precursor, which will convert this adsorbed precursor 1 into a new activated surface. And again, I do a purge. So I wash out all of the non-reacted precursor B, and I have a first atomic layer being deposited. There's quite some tricks behind this, but the process is I would use an aluminum containing precursor which would react with an OH surface, and then I will use a water or an oxidizing species to rehydrolyze the aluminum, and then I'll have again my aluminum precursor and hydrolyze, and aluminum precursor and hydrolyze. So this is what is basically happening, and we can see that depending on the amount of surface sites, I will have a full occupation. If there is no reactive site, I cannot react. If there is a reactive site, it can react. This is where the cleaning comes in. The ALD process works well on OH groups. If you have OH groups on the surface, most of the precursors will react with that surface, and you will have the conversion to the reactive site. There's a complication that the precursor may be too bulky, and that you don't have a full monolayer coverage because of a bulky ligand or because of too few reaction sites. But it's more important to understand, and this will take us too far, but this is an important one. You can have a variety of growth processes. In the first case, so you have a limited nucleation, but then in the second cycle of two processes, you fill in the empty spaces. So you basically, the surface reactivity is higher than the reactivity of the deposited layers. And only if the surface is fully covered, you will have the second layer being grown. This is truly monolayer by monolayer growth. In most cases, you will have a situation like this, whereby, I mean, you have a partial absorption on the surface. You convert this surface and make it susceptible to an absorption of the second precursor, and you have sort of a hybrid growth whereby the film gradually closes, but you don't have a first fully closed layer before the second layer is closed. But all this is depending on the surface termination. Now, if you have a surface with without any OH group, so in particular an hydrogen terminated surface, then you may have one nucleation site, and this surface is more reactive than the neighboring surface, so you will have an island-like growth and a pore growth. So that as the two examples for where you need an OH terminated surface and where you would need a hydrogen terminated surface. And then a short connection to last two classes. A lot of the characterization techniques that were described in the last two classes are being used to the characterization of surfaces and thin films. So contact angle measurements allow you to do an assessment of the hydrophilicity, the hydrophobicity. Cyclic voltammetry can tell you something about the goodness of passivation, how closed is your surface. Infrared gives you information on the chemical groups. The time of flight, secondary ion mass spectrometry or secondary ion mass spectrometry alone gives you information on the chemical composition and the layer closeness. Raman gives you also, like infrared, information on the chemical groups. Zeta potential measurements will tell you something about surface charge. And then we're going to fill into techniques that tell you more about the layer thickness. So the ellipsometry, X-ray diffraction, X-ray photoelectrospectroscopy give you. So there's some information here. This is a slide that you've seen I think in the presentation of my colleague Caroline Jans. So I'm not going to repeat that, but there's just two techniques, or at least one technique that I would like to highlight here, because I'm pretty sure that she did not touch on that one. And that is a technique that is called light scattering. And this is a concept that is used to identify particles on a surface. So the pie-shaped segment is just a segment from a wafer. It operates on full wafers, but this is just for the graphical representation. And from the top, you're basically shining a laser on top of the surface. The surface is reflecting, so the laser beam will basically scatter from the surface, and we are measuring both in plane and perpendicular to the plane. So whenever it's a shiny surface with no particle or no defect on the surface, the light will reflect in the two components in a specific direction. Now if there's a particle on the surface or a pit in the surface, but let's consider a particle for now, the laser will hit that particle and the light will scatter in a different direction than when it reflects from a mirror-like silicon surface. So we will measure a different component in plane and a different component in the perpendicular direction. By correlating this to the